Okay, so today we are happy to have Dr. Sergiy Nesterko from Fidelity. So Dr. Nesterko is Vice President at Data Science. He got his PhD from Harvard Statistics in 2012 with research interest in graph-based methods, model selection, and robust decision theory. And before he joined Fidelity, he has like extensive data science consulting experience. And now he is leading a team focusing on fixed income within the Fidelity, within the AI investment management and planning center of excellence at Fidelity. Okay, so without further ado, let's welcome Serge to give the talk.
Great, thank you so much. Thank you, Professor Su, for the introduction, and thank you and the section for statistical learning and data science for the ASA for your invitation. I really hope the audience finds this talk interesting. Thank you very much. So with that, let me share my screen. All right, so let's see. Can I get a sign whether you can see my screen?
Yes.
Great. So just to add to the introduction about our team is part of the AI Investment Management and Planning Center of Excellence at Fidelity Investments. And yes, we focus on partnering primarily with our stakeholders in the fixed income part of the asset management business in order to research and create data science and statistical approaches and models that add value to the business and its shareholders. Specifically, we have done work understanding and modeling how value gets assigned and exchanged in the markets in order to add efficiencies to how the business operates in the respective markets, specifically in the areas of trading and understanding market risk. And we're also engaged in some work researching how modern data science and machine learning methods could be used part of the quantitative investment process. That's just to add a little bit to the introduction. Before I start my talk here, which is the title slide is here, I just wanted to really quickly thank, if any of the team members are online, I wanted to thank for our team members for your inputs, which inspired much of today's presentation materials. Specifically, I'm not sure if Rebecca Kroll or Matt Fernandez are on the line or any of the others who've helped you know who you are. Thank you for that. All right, so this is for the acknowledgements. And again, thank you very much, Professor Su and the ASA for having me. So with that, the title of my talk today is called Production Data Science and Industry Computational Methods and Opportunities. It is centered around the short to medium-term projects that we do that for the purposes of this talk, let's call it production data science. And in this talk, I'll share two computational overall methods or approaches, call it two computational keys to performing production data science work, along with a couple or a few what I think are interesting and exciting open areas of research that are associated with these methods and also with production data science work that we do. Okay, so this is the quick summary of my talk. So the table of contents is then split into three parts. One is introduction. Hopefully we just covered that. So we just need to go through the second two parts. And the second part is called research and development topics. And in this part, I'll share these two computational methods. Let's call them computational keys for the purposes of this talk to performing production data science work. And the first key is stated in the first sub-bullet point, and it has some language here, which hopefully I'll introduce in more detail during my talk. But let's call it here as looking to improve reproducibility of computational reproducibility of the models we work on through this process called machine learning operations via representing the models that we work, the computational workflow of the models that we work on through this construct called Directed Acyclic Graph, or DAG, which is listed here. And what I suggest here is that this computational representation really helps streamline our work and guarantee computational reproducibility and lay a strong foundation for something called computational replicability of the models that we work on. And I'm hoping to introduce these terms in much more detail during my talk. Now, the second sub-bullet there talks about the second computational approach, or so to speak, computational key to doing production data science work, which essentially just says we want to use as many and as much low-code tools in our work as we can to do our work, with a caveat that we try to be aware that more often than we would like, low-code tools don't often take us to this production data science grade model. So we want to be aware and know what we need to know to do in order to fill that gap and make our projects incrementally progress in case low-code tools don't get the job done for us. And I'll provide an example here in this section of a model that's used in production applications in financial markets, where low-code tools get us almost all the way, but we do need to know a little bit of extra knowledge, a little bit have a better understanding of the methodologies in order to get the model to the full production. So this is the second bullet. I hope you'll find it interesting. This has to do with primarily computational methods, but also we open one open research question around the first method, around the DAG representation of the computational workflow, with which hopefully I hope some of the audience may find interesting. And in the third part of the talk, which I call production topics, I really share some of the very applied approaches we do primarily around adding automation to data selection and model retraining in production, and also adding automation to model selection in production. And I hope really to open a number of really interesting open research questions part of this section. So this is my table of contents. And without further ado, let me jump into the first section, which as we just noticed at the table of contents, I called reproducibility and MLOps. And that's, okay, I have a raised hand. So should I pause here, or what is?
Let me see. Okay. Jonathan, you're able to talk, I guess. Yeah, you can have any questions during the talk.
Of course, please.
Yeah. Or you can type your questions in the chat box. I guess that's probably the response from at the beginning, that you were asking if we see your screen and so on. And yeah. So
that's, we do see. So may I proceed?
Yeah, please.
Okay. So here's the first part, which is the first computational methodology for production data science work that we do, which I called here reproducibility and MLOps, the first computational key. So what is this? Let's try to define here, and what do we mean by that? And this slide here is supposed to cover the takeaway of this section. So let me try to go over it and summarize really the takeaway of this section. So in industry, an industry data science team, including ours, we perform research on our models in order to put them in production, and we'll define what we mean by that more over this section. But in order to reach that production outcome, we face risks of events that may prevent us for reaching that production outcome, and we call that production risks. And they actually include situations where the model that we do research on is either computationally non-reproducible or computationally non-replicable. So the likelihood of that creates a certain risk. And what I posit in this section is that representing as early as possible, either conceptually or in a very hands-on fashion, the computational workflow of the model or an algorithm or an approach that we research via this construct of a directed acyclic graph that represents the computational steps of the model as certain tasks that feed information one from another, can help mitigate non-reproducibility and non-replicability risk, and streamline our work. And also, I believe that there is an interesting open question here is, what kind of research could we do by conceptualizing the workflow representation of the model that we research as data, and analyzing it for patterns and looking to see how can we do research on computational reproducibility and replicability using DAG representation in itself. So let me delve into a little bit of details. I did introduce quite a bit of jargon here. I hope to make it more clear in this section. So what do we mean by computational reproducibility and replicability, and why do we care? Why should we care, especially in production data science work? So for this background slide, I borrowed the definition from a report on reproducibility and replicability in science from the National Academies of Sciences, Engineering, and Medicine from 2019, and that's the reference at the bottom of the slide. So, and here it's quoting verbatim. Let's define, for the purposes of this talk in science, computational reproducibility to mean computational reproducibility, which is obtaining consistent computational results during the same, using the same input data, conditions of analysis, and methods and code. Essentially, in my understanding, this means if you have a certain algorithm or an approach, you plug certain inputs in and you get stable output out, almost in a sense of numeric stability in some sense. Computational replicability is a broader definition. It means obtaining consistent results across studies aimed at answering the same scientific question, each of which has obtained its own data. So this is what we have for the definitions in science. Why do I say bring them here into an industry-focused presentation? Well, because for the purposes of this presentation, I propose to adapt these definitions and only slightly change them so that, and I propose that they are valid in the world of industry as well. Specifically, for the purposes of this talk, let's adopt the definition of reproducibility as exactly the same as from the report cited on the previous slide. But computational replicability, let's change it just slightly to change the word studies to model runs in production, quote unquote, and the word scientific to business. And so then our definition for the purposes of this talk would become replicability would mean obtaining consistent results across model runs in production, aimed at answering the same business question, each of which has obtained its own data. So why is this interesting to us? And also then there is a question, what do we mean by model run in production, this new change of language that we just introduced? So it turns out that after a model passes a research phase, which could be of variable length, it is ready to be used to address its intended goals. For example, make business critical inferences, predictions, recommendations, optimizations, and so forth. And to do that, what happens is models undergo this process of being transferred from a research environment into a production environment, and that process can change depending on the particular setting and the practices of the particular either organization or the team where you work in. But what conceptually happens is in that production environment, the models are quote unquote left alone to repeatedly execute against a so-called up-to-date live data feed. And that time period when a data science team does not touch this live model that now exists as an algorithm on its own in production is important. I suggest it is important because that allows the data scientist who say worked on this model to either spend less time checking on the model's results or focus the attention of a data scientist on more interesting questions like working on another model or writing a research paper or other areas of interest. So it turns out that there's a process in industry that is practiced in order to translate a model from a research environment or a research phase that, say, our team works on a model in a research phase into a production environment, and it's called machine learning operations, or MLOps, and that's the second bullet here. And here we borrow just a definition from Wikipedia just to provide a description of this process. And it is, Wikipedia states that this process is a process of taking an experimental, and for our purposes, let's say a research grade machine learning model into a production system. And it really takes a village in a sense that when an algorithm is ready to be launched, this process, MLOps, is practiced between data scientists, DevOps specialists, machine learning engineers to transition the algorithm into production systems. And it turns out that it's important, this fact that it takes, quote unquote, a proverbial village to translate the model from a research environment to a production environment. That's actually notable. Why is this notable? Well, it turns out that in this process of kind of lift and shift or translation of this algorithm or a method or a formula that we've developed in the research environment into a production environment, it is a non-zero chance, as small as it is, but it actually may happen, that the model may actually lose its computational reproducibility. So the intended numerical output of the model in the research phase may not be the same as the final product or these iterations in the production environment. And it actually turns out that that creates a risk. Reproducibility is a necessary condition for moving a model into production. So ideally, you never want your model to lose computational reproducibility in this process of research as it moves into production. And it is, theoretically speaking, it should be impossible to deploy a non-reproducible model into production, because if the model loses its computational reproducibility, really you plug the same input in and you are not sure what output you're going to get, essentially speaking. So that's a necessary condition for moving the model in production. Interestingly, computational replicability is a necessary condition for keeping the model in production. So once the model is now left alone, quote unquote, in production to generate value on its own, there exists a risk, and it's a very existing and much more prevalent risk, that the model may either gradually or suddenly lose its replicability. And that means that it is not really, once it's non-computationally replicable, it is not delivering the replicability metrics or answers, and no longer answering the question that it's aimed to answer. And that creates a risk of it being taken off of production back into research or being discontinued. So those are material practical considerations. So why should we care? And that's, again, we care about that for our production data science work, because we want to understand the factors that enable our models to generate value in production for as extended periods of time as possible. So here's an illustration. And in here we suggest, as we've mentioned before, that this necessary condition of computational reproducibility should really be maintained between the research phase and the production phase of the model as much as possible. And it turns out that, again, settings change, settings differ, and this illustration shows us that in R&D or in the research phase, you typically have more data to work on researching or ideating on a model. And this shows 4 sample projects that our team performed. And in the research phase, you typically have more records, and in your each production run, you have typically a somewhat smaller number of records. And so even though it is, of course, a necessary condition to maintain computational reproducibility, but it doesn't always happen as this algorithm moves from this setting of running on a larger number of records to the setting of running on a smaller number of records. And our team find it very useful to try to maintain that computational reproducibility as much as possible, especially moving between research and production phases. So what do we do to address that? And here's our first computational key, as as was previewed in the first slide, to analyze and ultimately mitigate production risks. I believe that it helps to represent, either conceptually or practically, our models, or the model that we work on, computational workflow, as a directed acyclic graph. And it represents the data tasks, the model tasks, the use cases, and replicability monitoring tasks as kind of computational steps that feed information one into another through these arrows, which essentially creates a directed acyclic graph construct. So let's illustrate this on an example of a linear regression model. And this example will also be used in another section. So how would we actually do this? So, okay, so, we have 4 colors here. We have our data tasks. So we collect data on X and Y on our variables. We perform any data transformations needed in our data tasks. And there's typically quite a few data tasks at the start. And then there is the model itself. We run the regression model, Y on X. We fit this model. And once we've run this model, then we have these use cases which use this model. And in this particular case, I just provide an illustration of 2 use cases. It could be more or less, or at least 1 use case, in case you have use cases for the model. So we could have use case 1, decision based on your expected value of your response variable, given values of your covariates. And use case 2, a decision based on the estimated error variance of your model. And it is in your final step, you check the decision outcomes, how many, let's say, how many of the attempted decisions were successful based on this, on the outputs of this model. And also you do check some technical, any technical diagnostics of your model that you would like. For example, root mean squared error, is it within acceptable bounds, and so forth. So just to illustrate, for example, of this model, as we'll see where to model, let's say, for example, a security returns, then if your estimated security return is sufficiently high, your use case 1 could be, let's invest in this security. And let's say use case 2, should for a particular security you have a high estimated model variance, then you might decide to route the analysis of the security to a market specialist to understand what's going on if your model produces a higher estimated error. Okay, so then just to drill down a little bit deeper, so let's decompose this DAG. So why is this useful? How can we use it? Well, it turns out that the top part of the DAG, the blue and the pink parts, the data and the model parts, primarily help us mitigate the non-reproducibility computational risk. Really, reproducing a model only entails the steps of data and model, data collection and model. And really, if you think about it more, you will really understand that really you only need the model itself to know whether it's computationally reproducible. However, in practice, oftentimes knowing or anticipating how the data may be collected for this model may actually help specify in more detail the computational reproducibility parameters of the model. Okay, so now that we've kind of gotten our computational reproducibility covered, then we can say, okay, well, production is typically triggered when a quote unquote sufficiently good model meets a use case, so that we kind of know that we can set up our model and feed its output into a use case or multiple use cases in order to generate value from the model. And then finally, models are kept online as long as replicability is satisfactory, and we've mentioned it prior. Computational replicability is a necessary condition for keeping the model in production. And then operationally, we need to consider possible scenarios for the different outcomes, whether replicability is satisfied to different degrees. That's not the focus of this presentation, but this computational representation does help think about these risks and work on them. All right. So this brings me to the end of my first computational key, so to speak, which is representing the computational workflow of the model we work on as a directed acyclic graph. And I believe that there is a good number of benefits of this approach, and they're listed here. we're able, using this approach, we're able to identify and mitigate these risks that we've just introduced, either computational reproducibility risk or computational replicability risks. Did we lose someone, or is this okay? Professor Su, should I continue?
Yes, we didn't lose anyone.
Okay, sounds good. Thank you very much. All right. So, and then we have ability to improve computational efficiency, actually, and or energy consumption. That's a subtle point in more practical applications, just to optimize how much, let's say, if you're using any cluster or any kind of collection of computers to move your model from research into production, it actually might help streamline that energy consumption and reduce the number of computational cycles needed to translate the model from research into production. And then I'm personally very excited by this idea. I hope it might be interesting to the audience here. We may use or be able to use this directed acyclic graph representation in itself as data in a way, and use it to research computational reproducibility and replicability using this DAG construct in itself. So, and then ultimately, I believe that the framing the computational workflow of the models we research can actually, in the longer term, help improve productivity and the impact of practicing data scientists. And of course, finally, last but not least, this approach is fully open source compatible. Of course, it can be either used conceptually or then used, using any open source language, Python or R, or any tool of your choosing. And it does offer, I believe, a view on standardizing computational representations in data science. But however, this approach does come with a caveat. Standardizing computational representations of the models we work on and mitigating these production risks of our models is kind of yet another thing that we as data scientists need to now worry about. So is this all just more things to worry about, or are there opportunities here? How can we use this as an opportunity to be more creative and be more inspired in our work? And this is where our second computational key comes in. Hopefully, I'm hoping to offer an answer in our second computational approach, which really is here. That's the title of my second part of my middle section of my talk, which really says we want to try to use as many low-code tools for production data science research and development as we really can. And let me define really quickly, for the purposes of this talk, what I mean by low-code tools. And really, a low-code tool is really any approach, tool, or a module or a software that helps you, or a math formula that helps you to translate a modeling idea into computer output by using a computer, by writing as few lines of code as possible or as little lines of code as possible. So that's a low-code tool. And the takeaway of this section is that it turns out that oftentimes low-code tools do take us all the way to production, but more often than we would like, they don't. And so they are an elusive combination. So performance in the sense of taking us all the way to production is sometimes an elusive property of low-code tools that we use. And in those cases, we do need to be equipped to know kind of what to do to still incrementally make progress in our projects on the way to production. And I'm going to try to illustrate this message in this section via an example where we discuss that available low-code tools take us almost all the way to production using actually a production model actually used in finance, but not fully all the way. And I'm hoping with that to motivate us to, just be aware of the fact that that what this computational key suggests is that we should try to use as many low-code tools as possible, but then be equipped in case they don't take us all the way. All right, so here's my example. It's a market liquidity model, a Bayesian regression. And I do take it from a published research reference here from Hasberg from 2009. And it is used in production in industry, or variants of this model are used in production in industry. So let's try to go over what does it do. And it's a very interesting model. In fact, let's just go through what does it do. So let's see. So we simulate 5,000 draws. So this is going to be a simulated data example. So let's simulate 5,000 draws or 5,000 rows of data. And roughly they'll correspond to about 20 years of daily historical let's say stock returns. And there's roughly 250 trading days in the year, so this is more or less realistic that 5,000 draws would correspond to 20 years of data. Now, how does this model work? So we generate two covariates. One, let's say x1, normal 0, 1, normal 0.1, 0.3 rather. And you can think of this covariate, x1, as daily market log returns. So for those of you who and I believe most people know S&P 500 or another major index. So think of it as a daily log returns of some major index, for example. And then we'll generate another covariate x2 as just a binary covariate. Essentially, it takes on just two values, either -1 or 1 with probability a half each. And -1 will stand for, in our discussion here, let's say for a bear day in the marketplace, and +1 will take for a bull day in the marketplace. For those of you kind of familiar in the market and with the market, so a bear day tends to be days where the markets are kind of selling off, and the bull days are the days when the market rally. That's kind of the intuition here. And so then finally, we will simulate our response variable y, essentially through our model here, setting the beta 1 and beta 2 coefficients and model error term to these values, as again, a normal random variable with the mean which is a linear combination of x1 and x2 with the pre-specified coefficients, and then also with a preset variance parameter here. And here, y can be interpreted as an individual stock's daily log return. So this is how this model is set up. And hopefully, as I describe this section forward, it'll become more clear how this model is actually used. And it is actually used in production applications. But mechanistically speaking, it's a fairly simple setup, hopefully, for most of the audience here.
Is it possible to ask a question?
So of course.
We have Q&A here.
Oh, okay. Yes, of course.
So there's a question from Michael that says, how do you, so there you mentioned something about low code. How do you define low? And what's the trade-off versus so-called no-code tools?
Oh, that's a great question. Thank you for that question. I would say the lowest possible code tool is no code tool. And I would love to hear from you also following this session, but I will assume that our definitions of no code tools, as in Michael's and mine, will be very similar. It's a tool where you don't have to write a single line of code. And I would say low code tools is tools where you have to write some code, but the more code you have to write, the less low code it is. And I would say it differs by application. I hope it's a directionally okay answer. And please feel free to provide any feedback in the Q&A if that works as an answer.
Hey, Sergiy, yeah, thanks. That's definitely a good answer. I guess so this is Mike Green. Nice to hear you. I was hoping you could talk about, if you had a second, about the trade-offs, because my experience is the less code is sometimes it's harder to get to customization and default. So I was kind of curious on your perception there.
Yeah, I mean, you're spot on, Mike, and it's great to have you here. Thank you for attending my talk. I guess in a way we are discussing these trade-offs in this section. Our goal here is to get into production, and in some sense, you do need that customization sometimes, or tweaking your model, as hopefully will become evident in the next slide and a couple other slides, where you run in a situation where your no-code tool or a low-code tool doesn't have all the features that you need. then you do need to customize, its output or its logic in some way. And then I guess let's say a data scientist needs to be, equipped to navigate that situation. Essentially I'm giving away the final slide of this section, but there's implication for data science education. So we need to know where to look for answers in case we need further customization, either in other tools or knowing some math and some theories for how to get an answer. Sometimes if a low-code tool doesn't have an answer, actually a no-code tool may have the full answer. Just a math formula might give you a full answer. So I wouldn't say that there is a straightforward answer to this question, Mike, but it's more just an awareness of sometimes customization might be needed, and one might need to know what to do in those cases. This is an okay answer, Mike?
Yeah, that's great. Thank you so much.
Thanks. Thank you for that question. All right, so let me proceed. So as we just simulated from this data, what we can do computationally, and what we actually do is, but for the case of this computational example, what we want to do when we test our model and figure out its computational reproducibility and replicability, we can just try to run this model. And what we can do is we can construct something that's called posterior prediction interval on an out of time sample. So we can split our observations into this proverbial 80 and 20 train and test split. So 80% of observations will be roughly 4,000 of rows of simulated data, and 20% of observations will set aside as a quote unquote not seen out of time sample, which will be 1,000 rows of data. We can fit this model on the train set and just see how does our posterior predictive interval do out of time, proverbially, in terms of being able to successfully predict your y variable given the values of the x variables. And I'm not going to cover in this talk the definition of a posterior predictive interval. It's a Bayesian statistics construct, and I highly encourage those less familiar or unfamiliar to explore. It's a very useful construct, and essentially what your model does, it tries to predict what we call a point estimate, a single number, and then the posterior predictive interval kind of tries to put a range around it to say, if I am a 50% posterior prediction interval, then 50% of the time of the interval, as I recalculate myself, as it is recalculated for each prediction, it should cover the truth 50% of the time. And it's often used to diagnose the numerics or computational reproducibility of the models that we implement. And this is what we do here, just to check. So we fit our model using three tools. One is the high code tool, so to speak, hand-coded something called Gibbs sampler using Python vanilla implementation. And again, in my talk, I don't define what a Gibbs sampler is, what MCMC or Markov Chain Monte Carlo is. I highly encourage those less familiar or unfamiliar with these concepts to explore what they are and how useful they are for modeling tasks. But we also estimate the model using other two tools, one tool called STAN and another tool called pyMC. Those two tools are considered generally low-code tools for Markov Chain Monte Carlo. Also available as Python packages with references down below here. And we see that, yes, indeed, since our data was simulated straight from the model, of course, we better be able to estimate our models well. And hopefully we did here. We're showing that the coverage rates for our 50% posterior intervals, the middle column here, are around very close to 50%, which is great. This is what we want to see. Then a number that's also generally tracked is what's the average length of the posterior interval, so the top value minus the bottom value. And in this case, it turns out to be 0.67, and it's the same between the three approaches. This adds confidence. That's great. We got our fitting routine going. However, the runtime of the models, interestingly, tracks with how low code versus high code they are. And we see that, of course, both the runtime and implementation time of our hand-coded Gibbs is longer, as maybe not as optimized, but really the STAN and pyMC tools really stand out here for this particular routine as a great introductory tool that maybe could even give us the outcome that we need and get us started on the model, which is fantastic. However, there is a wrinkle here, and the wrinkle is that typically that covariate X2, it isn't really reliably observed in the market. Remember, X2 was standing for a bull day or a bear day, and there may be some data feeds that may be providing that number, -1 or 1. However, generally it may not be as available. So as modelers or as data scientists, we may need to turn this variable into something called a latent variable. And also, I'm not defining what a latent variable is for the purposes of this talk, but for those less familiar, I highly encourage you to either follow up with me after or look it up. It's essentially turning it in the view of Bayesian statistics into a parameter, and we try to statistically infer for each day what is the most likely value of X2? Is it -1 or 1? And it turns out that hand-coded Gibbs works okay for that setting. We changed the algorithm a little bit for the fitting, and it runs longer. It runs for almost 2 hours, but it produces reasonable posterior predictive interval coverage rates, and it does have a widened average posterior interval length because we now have this added uncertainty of the parameters. But STAN and pyMC, they actually don't have all the features that we need for this particular version of the model. And it turns out that this is the model that is used in production and industry, not the first version. So in this particular case, we do see an example where very prevalent existing tools actually don't quite have the full features that we actually do need for a production model. And what happens in STAN, and we do use STAN, and also I had a privilege of taking even a class from one of the people associated with its creating, Professor Gelman. So this tool is a wonderful tool that really helps accelerate Markov Chain Monte Carlo sampling and fitting of the models. But in this particular case, the model actually needs to be amended for this tool to work because STAN does not support discrete parameters. And X2 is, technically speaking, now a discrete parameter. It only takes on values of either -1 or 1. And in order to achieve a very competitive posterior coverage rate and a posterior interval average length, and also it runs faster, STAN does need to change the model a little bit. And it turns out, once you do that, once you assume X2 continuous and modify your model, this actually changes the dynamics of how you estimate this coefficient beta2. And if you do believe the model, if you do believe that every day there's only a binary state, whether it's a bull day or a bear day, rather than a continuum of these, of a transition between a bull and a bear day, and then it matters to you because beta2 has an interpretation of something called a market liquidity cost value. So that's essentially the cost of trading, as they also call it sometimes in some applications. So, and I can go into more details after the talk in the Q&A. In the interest of saving time, let's just, let me hope that I convinced the audience here that in this particular case of a more realistic production model, low-code tools don't take us all the way because of a feature, lacking a particular feature that's needed. So this is the conclusion of this section of the talk. So this is our second key, and hopefully a brighter computational key in which computationally we should aim to save us time and use as much low-code tools or even maybe no-code tools as possible, as long as we keep in mind that sometimes, and more often than we as data scientists would like, these tools actually are unable to take us all the way to production. And in that case, we as data science teams and data practice and data scientists need to know kind of what to do in order to keep incrementally progressing in our research efforts to reach that production outcome in case low-code tools don't get the job done fully. And the development of these tools is really a multifaceted issue. It is a community effort, which is fantastic. In the open source domain, Fidelity also has an active presence through a range of open source low-code tools. But what should we do in cases low-code tools don't take us 100% to production? So faster implementation definitely creates well-justified incentive and a great solution for data science practitioners to use low-code tools. However, I believe that data science education should include training on what to do when a low-code tool runs into its limits, and so that the data scientists are trained to be aware of how to incrementally proceed in the research in order to reach that production data science state of replicability. And of course, open source tools have an avenue of submitting feature requests through the web and the conference presentations in the open source domain, but is there a better way? And it really is an open question that I also think about and invite the audience to think about. All right, so here's our first section, which is just concluded. And in it, I've shared two computational approaches, or so to speak, two computational keys to doing production data science work, along with one idea for a research direction around the representation of the computational workflow of our researched models as a directed acyclic graph, and also some considerations for practicing data scientists for how to apply these approaches. Now, in this next section, and this will be hopefully a shorter section so I don't run out of time, is just sharing some of the practical approaches we do for data selection and model selection in production. And here I'll go maybe a little bit faster just to make up some time. So in this section, automating data selection in production, what I'd like to say is it's common to have automatic model retraining in production, and that is a situation where more data kind of is collected in between the moment of time that, say, the original researched model was deployed in production. Say time goes by, more data is collected, and so it is common for actually the model to be actually automatically retrained at some increment in time. But what happens is due to the various circumstances which result in the change in statistical properties of say the data feed that's going to the training data, what might happen is, in a situation of a concept drift might happen, is the data may not be as amenable to model retraining in production. And I hope to cover this subject in more depth in my JSM talk later in August. So for those of you in audience, and if you are at JSM this year, I hope to make it there, and I hope to see you there in that talk. But for the purposes of this section, let's just assume that it does happen. Models do get retrained in production automatically, and it does happen that the data that feeds into your refreshed model retraining is not always as stable. So what do we do in that case? And here I'd like to share some of the approaches that we utilize, and also open some research questions for how can we automate these processes better. What is common to do is, in case there is a well-defined period of a part of the data feed that doesn't fully correspond to the current situation, say in the market or in the system that you're modeling, is to exclude that data from training. And that's a little counterintuitive, as typically, and I hope in the audience most would agree, is that more data is typically, or generally speaking, should be better for the model to learn better and to train better. And of course, there's theory that supports that. But in this setting, it actually could be better to actually exclude the data. And what happens is, in that case, with a human review, as is often practiced in order to mitigate some of the potential mischoices and the operational mischoices of excluding the data, with some human review, the data is excluded and the model is retrained. And here's an illustration of that. So let's assume in the model from the prior section, we have a temporary period of increased volatility, or the error term variance, in the feed. And then as we're nearing the end of that period, the volatility, or the vol, as they call it in finance, the vol has decreased. So at time 0 here, this is your time when your prior model was deployed in production, and time, say, 900, you can think of it as hours, for example, you're retraining your new model. And so what happens is pretty, as a standard approach, we might want to exclude this period of higher volatility, because what happens if you do include it in your training, you have extra wide prediction intervals, which are shown by these extra wide shaded areas. But if you exclude that data from training, and this is our next slide, you actually end up with narrower prediction intervals and better coverage rates. As this next table illustrates, your algorithm also runs faster because you've excluded some data, and it fits faster. You have narrower posterior prediction intervals and better coverage properties if you're able to successfully exclude data from your automatic model retraining. Now, a question here becomes, and here I posit that this is an open research question, is how can we add more automation into this process? Specifically, obviously, this template solution that I've just presented, obviously, it hopefully sparks quite a bit of questions. How can we do better? Given a general model use case specification, can we automatically detect which data could be ignored from retraining? And could we provide that as a hint to a data scientist or a machine learning operations specialist reviewing model retraining? What low-code tools are available to address this production need? I would be really curious to learn from anyone in the audience. Okay, so really quickly, hopefully, the second subpart of my production questions is how can we add automation to model selection in production? So, of course, now we've discussed model exclusion from data exclusion from retraining, from automatic model retraining in production. That, of course, assumes the same, say, functional form for the model that you are retraining. But maybe there is a way to even shift or change the functional form of the model altogether in your retraining. And that's a very relevant question for us. So here, just in spirit of time, just to share, this is something we work on and we use, is we're inspired by this concept of transfer risk. And here's a reference on the slide down below. And one way to select models in production is to provide a hint or a suggestion to, say, a data scientist or a machine learning expert to look at this metric transfer risk. Essentially, we can think of it simplified to a bootstrapped test set model error, or even just down to test set model error, really, and then reason about it and inform that automatic model selection on the next retraining. And here I'd like to illustrate very quickly this approach just through this quick plot, again, based on the simulated example. So as your new model is just retrained at time 0 here at the very leftmost side of the chart, as we move forward through time, we can keep calculating model error or bootstrap model error and seeing what the bootstrap interval may or may not tell us on an ongoing basis. And as that period of higher vol starts to kick in, we obviously start seeing model error creeping up, and it's going up. And as that higher vol period starts to go down, of course, we're starting to see this chart kind of capping down and starting to nod down. And this may be used by a machine learning experts on retraining to make decisions for what model could be more applicable in a particular regime. All right, so here's I'm nearing my wrap-up time, and I started a little later due to some technical difficulties dialing in. Thank you for allowing me for a couple more minutes to wrap up my hour-long presentation. So what are some of the conclusions of this part of this section? So in production, model selection concurrently with model retraining is very much an ongoing topic of interest. How can we add automation to this process? How can we optimally inform model selection expert of the risks associated with model selection at model retraining time or just prior? Given model use case specification and a particular, or in some generality, a model family specification, let's say an exponential family or another family of models, can model selection be performed as a well-defined optimization task? And do we think as a community that it can be fully automated altogether with maybe no human, proverbial human in the loop at all, with human in the loop here in this case being this machine learning expert or data scientist kind of looking over what's going on coming up right to the automatic model retraining? And last but not least, and especially I think this is relevant for financial markets, even thinking about the recent Federal Reserve Bank rate hike by 75 basis points, or situations like March and April 2020, how can we ensure robustness to test data stresses in this process? And I would think that this may not only be relevant for financial markets in terms of test data stresses, but it is definitely very relevant for financial markets. So this is my wrap-up slide. I'd like to recap really quickly. I shared two computational approaches, or two computational keys that our team uses in our production data science work, specifically using a directed acyclic graph representation for the computational workflows of the models we research as a way to streamline our research activities and address non-reproducibility and non-replicability production risks of the models we research. And also, I shared one associated research question of potentially using DAG as a subject of research in itself, DAG representation, to research non-reproducibility and non-replicability, or rather reproducibility and replicability. We always want our models to be reproducible and replicable. I've also shared another computational key, which is using as many and as much of low code or no code tools as possible, while keeping in mind that more often than we would like, we may, as data scientists, face situations where our low code methods or our math formula that we have developed that works in 80% of cases, but may not work for the 100% of the needed cases for production, might need customization. And how can we be equipped and trained as data scientists to know how to make incremental progress in our research efforts towards production in those cases? And then, as in my other part of the talk, I shared a few open research questions that I believe are open research questions, and I'd be really looking forward to any feedback and pointers in any directions there. In terms of adding automation to data selection for model retraining in production, and also adding automation to model selection in model retraining in production. So this is a recap of my talk. Thank you very much. Thank you, Professor Su. Thank you, the ASA, for inviting, and thank you, the webinar participants for attending. I hope you found it interesting. Here's my email in case anyone has any questions. Feel free to contact me. This concludes my talk. Thank you very much.
Thank you very much, Serge. Let me stop recording and move to the Q&A session.